So a little bit of review before we look at log graphs, log functions, the graphs of log functions. So this is from back in chapter, chapter 1 even, and then you looked at it again in chapter 3 because it's a quadratic. And what do you think? Just stop the video or think about this before I say much more. And what is happening with this function? So I'm seeing it's shifting right 3. So this is a parabola. It's shifted right 3 because it's opposite. It's being stretched, and then it's going up 4, and it's being stretched vertically by a factor of 2. All right, then this one, stop the video if you want and think about it, and then come back and listen if you want. I see an absolute value function. The position is shifted left 1 because of the minus and minus, right? It's been shifted down 4, and then I've got a vertical compression by a factor of 3, and it's been reflected around the x-axis because of the negative. Okay, so it's upside down, it opens upside down. The vertex is at -1, -4, and it's got instead of going down 1 over 1, down 1 over 1, it's going down 1 over 3. So it's much wider than normal. Okay, so this applies to our new learning too with logs. So part of this is going to be able to find the domain and the vertical asymptote of a log function, and hopefully relate it back to exponentials too. So what I did on this slide is I graphed here. I don't know if you can see this here. I got my pointer going. Here's the 10 raised to the x power. It's an exponential function. Here's log base 10. And then here's the graph of the line y equals x. I'm hoping what you're seeing is that they are inverse operations. So if this is x equals 0, 1, this is 1, 0. And we could find some others. If the graph was a little bigger, I could do 1, 10. Then I would see 10, 1 way over here. But of course, it doesn't show us that. So these are inverse functions. And if you can think about that, if I remember how we find inverses, if we have y equals 10 to the x, I'm going to switch x and y, 10 to the y. And then how do I unlock the y? Well, I do the log of both sides, right? Or rewrite it as a logarithm. So log base 10 of x equals y. And that's how we came up with their inverses. What else do I want to do? Oh, I know. I want you to make sure exponential functions have horizontal asymptotes. Log functions have vertical asymptotes. And that kind of makes sense if the range, or if the domain of 10 to the x is all reals, and that new range, remember we switch x and y, so the range for the log function is all reals. And if the range for the exponential function is from 0, doesn't include 0 to infinity, that's the new domain. The domain is 0 to infinity because they switch. So there's a vertical asymptote happening at x equals 0. Doesn't include it, that's where it is, okay? And you can kind of see that if you think about the transformations. If I have log of x, that's not shifted left or right. It's just right at, so the vertical asymptote happens at 0. We can't take the log of 0 because that's not in the domain, okay? So then what I did is here, can I see, here, let me, can't quite see what I'm writing when it's underneath all of the tools here in this applet, or in this app. So what I graphed is I graphed 2 to the x. So 2 to the x here, let me go to the pointer. So here's the 2 to the x, here's the log base 2, and then I also graphed 10 to the x and log base 10 of x. And see how this is just got some kind of vertical compression. It's not growing as fast as 10 to the x. And the same thing here. This has got some vertical stretch going on, right? It's growing faster than log base 10. So how do we get that? How do we figure that out? Well, for the log graph, because that's where we wanted to. I mean, how do I write this? How do I write y equals some number 10 to the x times 10 to the x to get this to be the vertical compression for A. I mean, that's going to be a little gnarly. I don't know why I want to go. That isn't really where I wanted to go. But we could figure out a number and do that. I suspect it might be a log. I don't know. I don't want to go there. It could be log 2. No, I don't want to do that. Let's not go there. I'll think about it and post it. But for the log base 2, here's what I'd like you to think about, and this will come back. So our domains are the same. Our domains haven't changed. Our ranges haven't changed. But if I have log base 2 of x, can't I write this? Here's what I wanted you to see. If I rewrote this using change of base, won't that be log of x divided by the log of 2? And can I write, and this is 1 times log x, so can I write this as 1 over log 2 times the log of x? So the vertical stretch is 1 divided by the log of 2. What is 1 divided by the log of 2? Looking at this graph, I think it's going to be bigger than 1 because it's got a vertical stretch going on. So let's see, what's 1 divided by log 2? Yeah, sure enough, I'm getting 3 point. So this is the same as 3.322 if I round. So with that said, when you do these equations, when you have to write a log graph, a log function, a function represent a graph that's a log graph, I would prefer that you leave it as 1 over log 2 rather than writing the 3.32. Okay, it's a more exact answer. It'll work better for you. Okay, so now we're supposed to graph these two equations on the same axes. Now, one thing I'm hoping you see, you're probably figuring, oh, he's probably just got inverses here. How can I show that these are inverses? Can you show me how those are inverses? Maybe think about it and come back and stop the video and think about it. I'll just do it right now. I guess I'll work with the exponential. So if x equals 10 raised to the 1/4 y minus 2, I'll add 2 to both sides. Do you like that save? And then I got to get rid of the 10 to the power, so I'll do the log base 10 of both sides. Equals 1/4 y. And then if I multiply by 4, do you see how I got that? Okay. I mean, I could have dropped in. Why don't we drop it in? What if I drop f of x into g of x? What if I find f of g of x? I just said that backwards today. Well, I'll do it this way. Why not? I said that backwards. I wrote it backwards, but it won't. It should work. Maybe I'll let you folks, if you want to, you can try the reverse. You can try g of f of x. So I've got 10 raised to the 1/4 of 4 log of x plus 2 minus 2. Well, the 1/4 and the 4 cancels out. 10, let's see, this says 10 raised to some power is x plus 2, and indeed I'm raising 10 to that power, so the log base 10 and the 10 to a power cancel out, so that leaves me x plus 2 minus 2, and then the 2's cancel out. So yeah, I get x. So f of g of x is equal to x. They're inverses. That's enough of that. You guys can try it the other way if you want. Here's the... So I graphed on Desmos. I went out and I graphed this, and you can see here's the line. Here's the line y equals x. And yeah, we can see that these are inverses, right? Notice that this has a horizontal asymptote of y equal -2. Notice that this has a vertical asymptote of x equals 2. So what I want you to get out of this when we get to the graphs is make sure you're looking for the horizontal asymptotes and the vertical asymptotes. People will get these confused on exams and get the question wrong. Okay, I don't want you to do that. I want you to look for those key features, because sometimes it's hard to tell whether it's a exponential growth, exponential decay. But if you're looking for or a log function, but if you're looking for the horizontal asymptotes and the vertical asymptotes, it's easier to see. All right, so then I wanted to make sure we threw something with a continuous growth and the natural base. So natural base, the natural log. How do we find the inverse of this? Well, again, maybe stop the video and try it yourself, or just watch it along. So I'm going to switch x and y, and I got to do the log of both sides, but because this is base e, the natural log really works well. So I'm just going to write ln x equals 2y. Isn't that nice? And then I'm going to divide by 2, so 1/2 ln y. And I don't know if I graph these. Here's the inverse. I don't know if I graph these. What would see something that looked like this, right? This is just some kind of horizontal stretch, right? And then so this would look something like this. This is some kind of vertical compression from 10 to the x, right? So if we wanted to write this as log base 10. Remember, this is log y divided by log e. And so I could bring that out. So that would be 1 over 2 log e of log y. That would be another way to write that. Oh, that's ugly. I like this. Okay, so that's inverses. They get reflected. Notice horizontal asymptote, vertical asymptotes. Okay, so now comes the part, one of those first learning targets, the first learning target I talked about, and we've seen this before, haven't we? Notice I can't take the log of a negative number, right? I can't take the log of 0. So what I'm solving is x has to be greater, x plus 2 has to be greater than 0. So x has to be greater than -2. So that's the domain. If we wanted to write this as an interval notation, open at -1/2 and then goes to infinity. And the vertical asymptotes happen at that place in the domain. So the VA happens at x equals -1/2. Okay, seems pretty intuitive. Sometimes people get it wrong. And then what's the domain and the vertical asymptote of this? Remember, we don't really give a hoot about the up-down shift, because that's just a vertical shift, right? So what we're really looking for is where it is 4 minus 3x. Where is that greater than 0? Because I can't take the ln of 0. So I don't know how to solve this. I guess I'll just subtract 4. And then we divide by -3. And remember, when we divide by a negative, it reflects it around. Or you're going to change the direction of the inequality. Where I was going with this was it's reflected around the y-axis, right? Because it's an inside negative. I mean, I could rewrite this as natural log of -3x minus 4, then plus 5. So reflection around the y-axis, right? So this log graph will look something like, I don't know, vertical asymptote of what, 4/3? So 1, 2, boop, 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 something like this. And it's got some shifting up going on. But it's going to head off this way, whereas normally log graphs head off like this, right? So reflection around the y-axis. So look for those. All right, so now comes to, for me, what's the best part of this section. How do we write an equation? I see, because it's in that log graph equation, we don't have to think too hard about this, but I do see a vertical asymptote at x equals -3. Now, I know generally these equations look like this. Y equals a times the log of some argument. Let's write x minus b plus some vertical shift. The nice thing about the David Lippman materials, most of them have k equals to 0, but we should check. Truthfully, guys, I'll never ask you on a test. I won't ask you for up-down shift. K will always be 0, but you want to show me. So where do I go from this? Well, I see a nice lattice point there. I see a -2, 0, and another nice lattice point right there, 1, -2. So we're going to use these and this information we've already got, x equals -3, to find an equation for this. First thing, start inside out. There's the vertical asymptote. So I know y equals a times the log of, here, let's get fancy, x plus 3 plus k. So I used the vertical asymptote to take care of the b inside. Now let's see if there's an up-down shift. That usually works pretty well if you use the x-intercept. So 0 is y. A times the log of -2 plus 3 plus k. Well, -2 plus 3 is 1. And we know 10 to what power is 1? Isn't that 0? So that means 0 times a is 0. So 0, remember that 0 there, 0 does equal k. So there's no up-down shift. Usually you can kind of spot that. See how this is 1 away from the vertical asymptote? If there's an up-down shift, usually that'll change. But like I said, I'm not gonna have you do that. So then now the only other thing is to find our stretch factor. So I know I got this other point here, -2 is y equals a, which I don't know, times the log of 1 plus 3. And we know k is 0, so we don't have to worry about it. Here, let me see if I can't move this all up to give myself some more room. So I got -2 equals a times the log of 4. And so won't a equal -2 over the log of 4? Now, so we could write y equals -2 over the log of 4 times the log of x plus 3. And that would be an equation for this graph. Now, the only other thing that might happen is if this is a multiple choice question, I probably won't give you log 4 on the bottom. What I want you to think about is that log 4 is the same thing as log of 2 squared. I can bring the 2 down in front. So that's -2 over 2 log 2 times the log of x plus 3. And notice the 2's and those 2's cancel. So -1 over log 2 would be the same function. Okay, so just be aware of that might happen. Might be something that happens in the back of the book. Please don't write this as a decimal. That's just so messy, and it's much cleaner just to write it as a fraction. So I think I got one more graph to use. I'm hitting some crazy buttons. Okay, so we're gonna start. So this graph, there's a couple of things happening here with this graph. It's our last one. Normally log graphs head off to the right like this, and I see this heads off to the left, so that tells me there's a reflection around that y-axis. I also see there's a vertical asymptote. Let's see, what is that? -2. So we know it's going to be y equals some stretch factor times the log of -x plus 2 plus some k factor, some up-down shift, which, as I said, this doesn't have. I'm not going to give that to you. But let's verify it. So I identified a couple of nice here. Here we go. So so I see that. Let's see, what do I got to do? I already got that, and then I'm gonna use that -3, 0 to not rule out that there's a vertical shift. So 0 equals some stretch factor times the log of -3 plus 2 plus k. So So 0 equals a times the log of, let's see, negative 3 plus 2 is negative 1. And then we change a sign. And the log of 1 is 0, so k does equal 0, so we're done. We don't have to worry about k. Let's do a little erasing here. And then, really, this is all about, do you understand how log functions behave? You know, that's what it all comes down to. So there's another point we can use. So negative 3 equals some stretch factor times the log of negative 5 plus 2 when we know k is 0. So it's negative 3 equals a times the log of, well, let's see, negative 5 plus 2 is negative 3. We change the sign. So a equals negative 3 over the log of 3. So I could write y equals negative 3 over the log of 3 times the log of negative times x plus 2. Now, one last thing before I leave this. Remember how so far I'm writing all these equations in terms of log base 10 with some kind of stretch factor. Remember how back when we first looked at, what did we look at? Log 2 and log versus log 10. There was a stretch how we could rewrite log. Remember how we could rewrite log? I could rewrite log base 2 of x as 1 over log 2 times log of x. Well, we could do the same thing. We could go the reverse here if we wanted to. We could write y equals negative 3 times the log. And if we think about this as change of base, it's the log of that divided by the log of 3, right? Because it's just multiplication. So we could write a 3 here if we wanted to. It wouldn't be wrong to. Sometimes it looks a little cleaner. I don't know. I like it the way I wrote it originally. That way it's easy. You don't have to think too hard. That is perfectly acceptable. I will groove on it. But if you want to take the extra step and support your work, you just can't show up magically. But if you like that better, that looks cleaner to you, do it. Okay, and that's 4.5.